That means we are handling like one of the most difficult, not difficult, most complex question it is. Okay, and I love to handle difficult question. Okay, Mickey Mouse question. Let Mickey Mouse from other university do it. Okay, McMaster, we do complex stuff. Okay, so we are going to do a moment about Z. Okay, so anything that is going anti-clockwise will be positive. Okay, now watch this. Okay, the 2,500. Okay, the 25,000. Is it to the element or is it to the neutral axis? Anyone? I don't want Mustafa to answer. Okay, Mustafa, no answering from you. I want other people now, Mustafa. Anyone? Hello? So minus 2,500 or 25,000. What is the perpendicular distance? Towards the element? Yes.
Is it to the element?
Yeah, there you go. Okay, it's towards the element because the perpendicular distance, right? This is the perpendicular distance. The perpendicular distance and the neutral axis are parallel. So you go towards the what? You go towards the element. Okay, so that is 0.5. Right? Then the next one, it is also going to generate anti-clockwise. Sorry, yeah, clockwise. Okay, so minus by 100 times 10 power 3. Okay, minus 1. Now, what is this distance? Anyone? Is it going to be towards the neutral axis or towards the element?
Neutral axis.
Neutral axis. Well, and the distance towards the neutral axis is equal to, so I don't know that number at all. So that value is, so I don't know this distance at all, right? So I don't know this. Yeah, so I need to find out what is this distance, right? So D is 205, right? Yeah, so 205, half of that. Okay, so 205 or 0.205 divided by 2. Okay, so hold on, did I get my norm? This is my moment about X. Okay, my moment about X. Okay, so this will be equal to 2,500 or 25,000 times by 0.5 plus by 100 power 3 times by 0.205 divided by 2. So it's 22750. Okay, 22 is minus 22750 Newton meter. So my direction, so it's minus is going this way, right? So when it's going this way, right? So it is going this way. Wait, is it going that way? Yes. Okay. So over here is compression. This here is tensile. Okay. So when we put into the formula where moment or stress in the y direction, z. Okay. So this will be equal to mx over ixx multiplied by y. Okay. So for this case, element A will be in tensile. Okay. And element B will be equal to 0. Right? Because it is spot on the what? On the neutral axis. So let me see, is there any other courses that I am missing? So did we do, so 16 is there? Let me see, is there any other Vx? Let me check first, Vx. So we have another V, right? Wait, let me, yeah, we have another V. So over here, right, we can see that we have our Vz, Vy. Okay, Vy is equal to 25,000 Newton. Now, question. If we were to apply the shear is equal to Vy over Ixx multiplied by Qx divided by T, will the element at A be equal to 0? In terms of shear, due to the 25,000.
No.
And what is going to happen about B?
A wouldn't be at 0.
Huh?
A wouldn't be at 0.
Yeah, I thought so also. Now, the problem is this. We are visualizing based on what? Thick wall analysis. That's where you think is 0. So now I'll do this again, okay? I'll do this again. So now I'm going to, when I was teaching this course for the second time, I also taught it, and then I realized, oh, Eugene, you taught them the wrong thing, and I'm so pissed off. So based on the view that we have, right, Vy is coming in this direction. Mustafa, do you still agree that it's going to be 0?
No, it would not be 0.
Why?
Because it's a wide flange analysis and it's coming from the...
Yeah, it's a thin wall now, right?
Yep.
So now that is why for this topic, you go to check, okay, very seldom you will get the correct answer because it's an integration of different topics. Okay, only McMaster students are capable. I'll boldly tell you that. Okay, I'll boldly tell you that only you guys are capable to integrate different topics. If you were to study this course in other university, they won't integrate. Okay, I want to integrate because I want you to be not just an ordinary engineer. I want you guys to become a what? What type of engineers you want to be? Anyone?
Elite engineer. Elite.
Huh?
An
Elite.
elite. Yeah.
Hidu. Bullshit, man. I want you to become super engineer. Elite. So stress at point A is not equal to 0. Right? If we view it from this view, right? I understand why you say it's equal to 0 because thick wall analysis. If we apply thick wall analysis, right? So if this is our shear direction, right? It always start from 0, go to the peak, and come down. Yes or no? Yeah, nothing wrong with that. If and only if it's a thick wall analysis, but we're not handling thick wall. We're handling. So that's why, in terms of shear, you have to be very, very, very careful. And now, I mean, based on this, I'm very sure that the shear stress at point B will be its maximum because point B is down here, or element B is here. Okay. Right. So now is the time of integration. So unfortunately, you have to recall everything that you studied from week 1 to now. Okay. So this part, that what we have just done, okay, what we have just done down here, okay, what we have just done in the analysis up to here, right? This is what I've taught this week. Okay. But to go to the next stage, right? To plot the calculate the stresses, we have to look at whatever gone on for week 1 to week 5. Okay, if you forget what you have learned from week 1 to now, okay, you will get some marks for your exam or for your term test. Okay, but it's not going to be more than 5 out of 15. I will tell you that. Okay, but that's where bending moment is easy for you all to recall because you all have learned from 2P. Shear stress is just yesterday. Right? So now we start integration. Okay, integrating there. So now we are going to analyze. Okay, we're going to analyze. So let's handle element A first. Okay, we're going to analyze.
Eugene, can I ask a question quickly?
Yes.
In the first view you did, when you did the bending moment, you said that element B was in tension, but it looks like it's on the neutral axis in your diagram.
Yeah, it's not. Okay, so if you look at, okay, if you look at this view, right, B is not exactly on the neutral axis. Can you see the offset?
Oh, okay, thank you.
Right, so that's why I drew. Now, Adam, you're not wrong. I've come across a lot of calculations, okay, when they just say this is equal to 0. Okay, but I don't want to teach that way because it depends on the thickness of the web, or the thickness of the section, okay, is not equal to 0. Okay, so our advice not to just like boom, ignore it. Don't do that. Okay, that's a good observation though. Okay. Look, but see something. Okay, very good. I like that. Okay, then we are going to look at element A. So let me get element A. Okay, let me get element A. Okay, so this is your element A. Okay, we are going to deal with element A first. Next week, next week, then we deal with element B. Right. So we know the distance from here to here. This distance is 75 millimeters. Okay, that is 75 millimeters. And if I look at the table, okay, okay, that's not okay. So what we want to find is stress X. Sorry, not X, stress Z at point A. Okay, at element A. So this will be my X, and this will be my Y. Okay. So now I'm going to tell you guys first, okay, this class will go over by at least 10-15 minutes. Okay, I do apologize. If you have other class to go, please go. Okay, as I said, all are recorded. Okay, so we have PZ divided by area. Okay, then we have our Y over IYY multiplied by X. Why I leave it blank? Because I don't know the direction yet. I don't know the direction right yet. Okay, so this is px over ixx multiplied by y. Okay, so based on where let's look at pz. Okay, so pz at element A will induce a compression. So you go down here. Okay, I know that this is what? Minus. Okay, then we look at moment about y. Okay, so you go down here. Moment about y at point A will also be what? Will also be compression. Okay, so you just put down here minus. And then mz, okay, mz. So we go to moment about z, okay, and element A will be what? Tensile. Now you all realize why I'm teaching you guys this way, right? Don't worry about the sign. Analyze, then put the direction in. Okay, don't like positive or negative. No, visualize the deformation. Okay, don't just trust the black box. Apply the vectors and you're good to go. Okay, sometimes you make mistake. Okay, so physically visualizing it is very important. Okay, so now this will be equal to, so PZ. What is our PZ? Our PZ is 100. Okay, so minus 100 times 10 to the power 3. And then we can get the area. Okay, so over here on the table, we can get the area, right? So the area is 5320 millimeters squared. Okay, so 5320 times 10 to the power minus 6 squared times 10 to the power. Okay, then we are going to minus my. So my is equal to what? My. So I have to look for the my value. 9600. Okay, so my. So we put the minus already. So 9600. Then we divide by IYY. Okay, so IYY. So IYY is 9.03 times 10 to the power minus 6. Okay, 9.03. Now, one thing I've learned is your transformation, right? If you construct, let's say, yeah, like for this case, let's say you don't have this. Okay, let's say you don't have this. Try to align your transformation similar to here. You get what I mean? Yes or no? Right? So this is my x, because over here, right, the second moment of area is related to the axis based on how they derive it. If you get it wrong, okay, yeah, okay, we get it wrong, yeah, we're in trouble. How come we did not consider the stress caused by 100? I think we did, right? Oh, she said, okay. Okay, now